pleasure to introduce one of our own. He was our own even before I was our own, or especially before I was our own, Ioannis Konstantinidis, who will talk about unclouding pollution maps. Ioannis, you know that it's only 25 minutes.
Yes. Well, thank you so much, and thank you to the committee for inviting me. I have to say, I may have been here before you, but I don't think that I was more our own than you are. So, right back at you. So, so this is, so we had an engineering talk, we had a math talk. This is a public service announcement. So I want to talk about the Houston Clean Air Network team. And I want to start off with something that I guess sounds like a joke. A philosopher, a mathematician, and an atmospheric scientist that walk into a bar. But that really did happen, and there's no punchline. It's just that we met a computer scientist and an environmental justice advocate, and that's how our team formed. We started to talk about ozone pollution. And so this is joint work with all of these people. It happened at the University of Houston. Some of these people are no longer there. Matt Tejada is now with the EPA Office of Environmental Justice, for example. But the mathematically adept in the audience might notice that there's more names than categories. It's a classification problem. We have grad students and other smart people, and they tend to do the work, so they should get credit. So special thanks to major sponsors, the Houston Endowment, the American Lung Association, and the University of Houston. And standard disclaimer, everything I say cannot be construed to in any way represent what their official positions are, and they are held harmless, right? So now that we got all that out of the way, the main issue, the main topic of our talk, the issue with ground level ozone. So ground level ozone, I mean, you probably have heard of this, but if you will indulge me a little bit, like I said, it's a PSA announcement. So ground level ozone is not emitted directly into the air, but it forms through a reaction of nitrogen oxides and volatile organic compounds in the presence of sunlight. Now, sunlight is something that we have a lot of in Houston, for those of you that have visited. And we also have a lot of major man-made sources of nitrogen oxides and volatile organic compounds. We have industrial facilities, petrochemical facilities in particular. Some of the people who talked before are familiar with those. Electric utilities, lots of motor vehicle traffic, chemical solvents, gasoline vapors, and all those good stuff. I mean, we're not the only ones that have these. Pretty much every major metropolitan area in the U.S. Needs this. So the problem is we get a lot of ozone, we get a lot of smog. And ozone is a highly reactive gas, which is good when it's high up in the atmosphere because it reacts with stuff that we don't want to make it down to the ground level and protects us. But when it's on the ground, it's the main component of smog. And when inhaled, it damages the lung membrane, it decreases the lung capacity, and it causes inflammation. So that's why it is regulated by the EPA, which sets standards for acceptable exposure. And this is what motivated us in this work, is how can we get the general public to have a better understanding and engagement with the actual problem as it exists in the area. And you'll see why this is a little bit challenging later on. So the EPA has developed an air quality index for ozone, and in order to compute that AQI, you measure the concentrations of ozone, that's in parts per billion, in mole, and you average it over an 8-hour period, because effects tend to be due to cumulative exposure. I mean, there's also acute effects, and it's actually very complicated. It's not well understood how the long-term health effects of ozone are related to exposure. There's some studies that show that heart attacks are correlated with high ozone exposure. There's a certain segment of the population who have asthma. Not everyone who has asthma, but there's a certain part that ozone acts as a trigger for asthmatic attacks. And that tends to have a delay. I mean, it's not that as soon as you get exposed, it's like a few hours to maybe a day or two later. But anyway, so for the purposes of the regulatory regime that the federal government has, each 8-hour period is classified as one of these categories: good, moderate, unhealthy, sensitive groups, and so on, according to a series of threshold values. And those values have not remained constant. The EPA issues new rules and updates those values, and the idea is to lower them as we learn more about the science, because, and in fact, the European Union has their own regulatory standards, and they tend to be a little more proactive and a little bit, the values are lower. The current rule in place since 2008 has the threshold from moderate to unhealthy for sensitive groups, which is sort of a minimum thing that you want to accomplish at 75 parts per billion. And it was a big, big fight to get there. So over 8 hours, if your average exposure was more than 75 parts per billion, then that was unhealthy if you belong to one of those sensitive groups. So the EPA standard says that that threshold should not be exceeded more than 4 days a year. Okay, that's to attain compliance. And if you see a map of the US where the areas that have not attained that standard are mapped, you see a map of the US that has the metropolitan regions. So the fact that Houston is not in attainment does not make us unique, but and we have been getting better. Everyone actually in the country has been trying to push things down, but the problem is that you need to have awareness in the public in order to push for the regulatory mechanism to move forward. So anyway, there's a separate standard that's based on 1 hour averages. So here's an example, Houston concentrations. I know, I had to go there, right? I mean, we had to go. So the 8 hour averages in this case were exceeded, and as I was saying, so this is 66, these are 1 hour averages. So if you average over the 8 hours, you see that starting at 9 o'clock, this time 8 hour period was problematic. So that was not a good day for you to be outside. So our goal was, how can we inform the public in a way that's more proactive and engaging than the current ways? And here's the problem with the current ways. I mean, it's not that we don't know what's going on with ozone. The Texas Commission on Environmental Quality maintains a network of 45 stations, and these are mapped here. And they collect measurements every 5 minutes. That's a pretty good concentration of measuring stations compared to other metropolitan areas. The problem is they make the data retroactively available, and they only report the 1 hour average for the previous hour, because that's all that they're obliged to do from a regulatory perspective. And in the great state of Texas, we like to keep regulation light. So that's you go there, you go to that website, and if you can navigate the 3-4 structures down, I mean, this is what you get. No forecasts, no location-specific estimates. You're basically, the data is there, but it's hard to access. Now, the EPA, on the other hand, does produce daily forecast maps for the actual quality index. That's their map for yesterday. You can tell when I compiled my slides. So the problem with that is, I mean, this is nice. This is what we would like to have. We would like to have something that the public can see that sort of pictures also like, a cloud, a radar map or something. But the problem with this is that it doesn't capture the dynamics of the pollution of ozone. basically what it does is it tells the public, if you live in this rather broad area, then, there's days that are good and there's days that are bad. But it doesn't show you how ozone is formed throughout the day, how ozone, it's not, a cloud analogy is not perfectly, it doesn't have the surface tension to form a cloud, but the concentrations do move in ways that we can capture. We have those 5-minute increments. We don't need to be stuck with this daily overall, and we can understand why, the agencies do what they do. They have a retrospective analysis that is their main charge. But that doesn't mean that we cannot do something that would be better. And so that's what we did. We put together an app, a mobile app for an iPhone and Android devices. And we have a website where you can go and you can see the map. And this is an example, this is historical data. The map will be produced real time with the data that we get from the TCEQ. But we also have the historical data so that you can go back and you can see exactly how the ozone formed and moved. And the reason we're doing this is because we want to have a better understanding of ozone in the area. If we want to go back and do epidemiological studies, or if we want to go back and do analysis of the data, we want to have this type of resolution and presentation. And with the app, we have location data. We could produce customized exposure averages for where you were during the day, rather than relying on the overall average that the EPA has produced. So, in a nutshell, this is what we set out to do, and this is what we came up with. And if you're going to be in Houston, you can download the app on your iPhone and know whether it's a good idea. But so what I want to do is, because this is the February Fourier talks, I want to talk about a little bit about how we did it, right? What's the method behind it? And what that connection is to the only thing that I know how to do in life, which is frame theory. And that took me a while until I learned. And I'm still not very good at it. But so there it goes. So the method. Oh, by the way, why can't we use the EPA method? The EPA method, because we looked it up, and it turns out that the way that they calculate they estimate the AQI is a 1-point regression on the current value at that station location. Basically, every station, there's a table that gives a slope and an intercept. You look at the value at that station, and you do your 1-point regression, and you get your AQI. Well, surely we can do better, especially if we've taken a class with John. So, and how many people here did take a class with John? Quick show of hands. So we can all do better. So this will be remedial. We'll just go over. The rest of you just humor us while I'm trudging through the meeting. So let's assume that we have an unknown f, goes from RD to R, and maps x to fx. Think of D as two-dimensional. We have a grid, latitude, longitude on a grid in the Houston area. It's close enough. So F is the measured density of ozone in that location. Okay? So we're given a set of n observations. There's 45 stations in the area, so n is 45. So we have these observations, we have these observed values for y, so we have y of n is f of xn. So can we estimate f at a given location there, right? You're there with your phone, I know where you are, I know your x, y. Can I tell you an estimate of what your ozone exposure is at that location? Well, Great, that's the most underdetermined problem in the world, right? So let's do it. Clearly we need to have something more, and we do have something. So gradually we're building up our prior assumptions, right? I'm not talking about priors in a statistical sense, at least not yet. This is just extra information. We do have an actual time series for every station. I mean, it's not just the ozone density we got at the time now. We have the ozone density values that we measured at all previous times. I mean, that could be in the order of 10,000 or so, I mean, going back. So there's an RP with P high, okay, but finite. I want to keep things simple. So, and computable. So there's a P that's high, and what we have is really, we have this time series. Phi of x is a time series for that location, right? So phi stands for feature vector. I cannot spell. I mean, English is my second language, so RP stands for feature space. Too much? Should I keep going? Okay, but that should help you keep track of the indices. I mean, it's you know, it helps with mnemonics. So here's the key assumption: phi must be invertible and known, because really, if you cannot identify, I mean, if you have two stations and they produce identical time series over the last 3 years, might as well module out and say they're the same. And it's not going to happen. So this is the setting that we're working with. Okay, so rather than trying to work with f on x, why not work with f composed with that phi inverse that exists? You know, we move to the feature space rather than working on the spatial, on RD. So what we're going to end up with is Creegan, named after Creegan, the South African mine engineer, which is well known in the geospatial the geology community. But we're going to get, so Creegan is basically interpolating in space, right? But we're going to get there through a feature space. So again, bear with me as I do some of these details. So here's the thing that I know, right? Finite frames. So what do I know? I know that capital phi, which remember it's the set of feature vectors that we had, phi1, phi. I know that it's a frame for its span in RP because everything is finite, so I don't have to worry about it. I mean, it will. I mean, if all the feature vectors are 0, then I'm doing this something wrong. So I cannot find out a way for doing calligraphic f. That calligraphic phi in LaTeX, so the space will be h. Otherwise, it will be cal phi. Here's some obligatory definitions. We have the analysis map, which is basically just the projection onto the frame elements. So if we think in matrix notation, right, I want to think of phi as a picket basis. Phi is a column vector, then phi transpose, capital phi transpose is a frame elements, and that's my analysis map. So I can define my frame operator, which is a square matrix acting on phi, or this decomposition. And there's also the Brownian or the Brown matrix, and that operates on the space of coefficients. Which remember, n might be 45 in our case, but p is I don't know. I mean, anyway, from 6 to 6,000. So here's a quick lemma, and what does it say? It says that we can figure out the linear functionals at least on that space. If what I'm doing is I'm looking at the linear combination, summation alpha sub P phi star sub P, then I can compute that alpha exactly. That's just something that has to do with the Brownian or the frame operator inverting it and the values that I know. Why is that? Real quick, I mean, it's just the inversion formula for the frame operator, because Y is really the frame operator acting on alpha, so I can invert that, and then just a quick algebra shows that if I don't want to work with n by n matrices, I can work with p by p matrices. That's all I'm saying. I can do this inversion in either the frame space or the feature space. So what does that buy me? Well, this phi tilde, right, which was the function that I was trying to estimate. If I can get this estimation for the phi tilde, which is it's now going to be exact on the span. I mean, if I'm in the span of the frame, if the feature vectors that I chose are rich enough in their diversity to span a space that captures all of the image of my space X in RP, then I'm good, because I can reconstruct, I mean, this estimation, this is exact now if I'm in the space. But of course, why should I expect that, right? So that's where pure frame pure subs and statistics come in. Says it's okay, you know. Let's say that we go from deterministic setting to a probabilistic setting so that we can get some estimates. There's a zero mean Gaussian prior for my regression coefficients. There's additive errors in the measurements that I get. So yi is f of phi I plus some error term that's got a standard deviation that's sigma squared. All you have to do is look at this equation that you had, and you have to add some error term there. And of course, if you think that your error is small, if you want to have, you know, interpolation, you know, sigma going to 0, that's the formula that you get. That's the formula. Equation 1 is the formula that you get from least squares estimation, basically. So that's why it looks familiar. If you want a Bayesian approach, you're scaling by the node. So what does that give us? It says that I can, so it tells me that that's the estimate that I will use. And that's the Creegan estimate as well. And that's a special case if you think about it, and that's what I'll talk a little bit from now on. That's a special case of Gaussian process regression. How does that? The Brownian is a mapping. Basically, you know, it takes your points in your space RD and it maps them to a scalar, which is the inner product of their feature vectors. So, if I can extend that to a kernel on all of RD, right? That's the kernel trick in machine learning. Then, you know, we don't need to have an explicit formula for these things. Everything in this formula that we're using involves the feature vector inner products. So I don't need to have explicit formulas for phi. I just need to have formulas for the kernel. And in the finite case, I don't have to worry about the frame conditions. In the infinite case, machine learning calls it Mercer's theorem, but it's just the decomposition. If we have a positive semi-definite function, then the phis will be the eigenfunctions for that, and the theory carries through relatively easily. So what I have to do now is I have to be able to extend these sampled values, right? These are now my sampled values on these pairs. if I can extend that into all of RD, I'm good. How do I do that? Well, here's one thing. If there's a common assumption that says, let's say, assume I have homogeneity. Let's assume that these inner products depend on the distance in RD. So there's a function h, and that's really what matters. This makes things easier because G becomes banded, and numerically you can say things, even computationally you can say things. So all I have to do is basically plot the inner products in the feature space of the xn's versus their distances in RD, see if I can fit a function there, then go back, build the kernel. Common choice is a Gaussian. That's really equivalent to thinking of the points as random variables and putting a random field on that structure on that. And so there's all sorts of ways that we can go with this. It ties into Tikhonov regularization if we want to do it in a different way. It ties in, but I think we get the picture. I'm looking at Lloyd again. He's frantically telling me we don't have time for a part. So I think that you won't complain if I stop here. And the last thing that I want to leave you with is I will take some time out of the traditional thanking the speaker in order to point that this is the golden jubilee for John Benedetto since he got his PhD 50 years ago. So So that's all.
Thank you very much, Yanni. For those of you who don't know Benedetto students, there is a lot of competition between them. And Yanni just mentioning these 50 years put himself at the very bottom.
I'm 3 hours away if I play.
Any questions or comments?
Those are, so you prefer the radial basis function method, I guess?
Well, we basically did it with the, yes, I mean, this is a radial basis
I was going to say,
function.
how does it work with your regular spacing, your regular data like you have?
Well, so that's, I guess that's what you would call future directions in our project. What we needed to do first was get something out. So there's a couple of problems that we run into this that were not purely math. You have to convince the people that are involved in this that you're not doing anything that's too fancy, because then they think you have a hidden agenda and you're out to get the industry or something. So and error plots and things like that don't necessarily work. But things by fiat, that's how they do it, tend to carry weight sometimes. So it's a good question, but this is not something that we have done yet. I don't think.
If you had other data, which you probably can get, things like traffic monitoring and even the reports, the EPA requires reports from these industrial facilities, but they're at vastly different spatial and temporal scales. Can this methodology be used to incorporate that information?
So we actually want to do that. We actually have talked to people to get measurements, especially on road data.
That exists.
The approach that we want to try on that, again, we haven't done it yet. I think fusion frames is how we would work with that, but I don't know how it would work. But we do have to think about how to incorporate the different scales, like you mentioned. But I think that we can have the same kernel. I mean, it's just you build the kernel differently. I mean, as long as you keep it becomes an independence condition so that you can add the kernels. But that's mild, I think, compared to what we're doing.
Well, let us thank our speaker again. please reserve your seats because we usually have a larger audience for our last talk for the colloquium, which will start in 15 minutes.